Hey everyone, Ivan here. Welcome back to our Computer Science Fundamental series. Today we're diving again in now another topic of algorithms and data structures, the powerful patterns that make computing efficient and effective. In our previous videos, we explored how computers represent information using binary and how hardware components work together to process this information. Today we're moving up a level to understand how we organize data and create step-by-step procedures to solve problems. Think about it like this. Having powerful hardware is like having a very strong person help you move house. But without a good plan for packing and unpacking algorithms and smart ways to organize your belongings, data structures, even the strongest helper won't be efficient. Let's explore why these concepts matter, even if you never write a line of code. An algorithm is a simple step-by-step procedure for solving problems or accomplish a task. They're everywhere in our daily lives, from recipes, assembly instructions, and driving directions, or all algorithms. For example, a recipe for a sandwich follows these steps. First, take 2 slices of bread. 2. Spread condiments on the one side of each slice. 3rd, add fillings between the slices. And 4th, press bread slices together. This is an algorithm, a clear and ambiguous set of instructions that produces a consistent result. Computer algorithms work the same way, just with data instead of physical objects. For example, a simple sorting algorithm might look like: first, compare the first 2 items. Second, if the first is larger, swap them. Third, move the next pair of items. 4. Repeat until no more swaps are needed. What makes algorithms powerful is that they're abstract. The same sorting algorithms works whether you're sorting numbers, names, or any other comparable items. This abstraction allows us to solve entire categories of problems rather than just specific instances. Algorithms are evaluated on several key properties: correctness, does it always produce the right answer? Efficiency, how quickly does it run and how much memory does it use? Simplicity, it is easy to understand and implement. Adaptability, can it handle different types of input? Not all algorithms are created equal. 2 algorithms might both correctly solve the same problem, but one might be dramatically more efficient than the other. Consider searching for a name in a phone book. You could start at page 1 and check every page. It's linear search. But you could open to the middle, see if your target comes before or after, and eliminate half of the book immediately. Binary search. Computer scientists use big O notation to describe how an algorithm's performance scales with input size. This matters tremendously because inefficient algorithms become impractical with large datasets. For example, O1 constant time performance doesn't depend on input size, like accessing an array element. O log n, logarithmic time, performance increases slowly as input grows, like binary search. On, linear time, performance scales directly with input size, like checking every element once. On at power 2, quadratic time, performance scales with the square of input size, like comparing every item to every other item. The difference between these efficiency classes becomes enormous with large datasets. With 1,000,000 items and On at power 2 algorithm might take days, while an On logarithm n algorithm finishes in milliseconds. This is why major companies like Google and Facebook invest heavily in algorithm optimizations. Small improvements in algorithm efficiency can save millions in computing cost. Data structures are specialized ways of organizing and storing data for efficient access and modification. Like algorithms, they're abstract patterns that can be applied to various types of information. The simplest data structure is the array, a contiguous block of memory with elements accessed by position. Arrays provide fast access to element by index. By adding or removing elements can be inefficient because everything might need to be shifted. Linked lists solve this by storing elements in separate nodes with pointers to the next node. This makes insertion and deletion efficient but sacrifices the direct access arrays provide. Stacks follows a last first out pattern, like a stack of plates where you can only take from the top. They perfect for tracking function calls, undo operation, or any scenario where the most recent item should be processed first. Queues use first in, first out, like a line at a store. They're ideal for managing tasks that should be processed in the order they arrive, like print jobs or requests to a web server. Trees organize data hierarchically with parent-child relationship, like family trees or organizational charts. They're crucial for representing nested structures and enable efficient search and sort data. Hash tables map keys to values using a hash function, providing extremely fast lookouts. They power dictionaries, databases, and caches throughout computing. Let's look at how algorithms and data structures power the technologies we usually use daily. Search engines use complex indexing, data structures, and ranking algorithms to deliver relevant results in milliseconds from billions of web pages. Social media feeds use recommendation algorithms that analyze your behavior patterns, social connections, and content characteristics to predict what will keep you engaged. Navigation apps use path-finding algorithms like Digestra or AidStart to calculate optimal routes through vast road networks, considering factors like distance, traffic, and route conditions. Video streaming services use compression algorithms that identify patterns in visual data to dramatically reduce file sizes while preserving quality. Machine learning algorithms find patterns in vast datasets that will be impossible for humans to process manually, enabling everything from product recommendations to medical diagnosis. Understanding algorithms isn't just for programmers. Algorithm thinking, breaking problems into clear, logical steps, is valuable in many areas of life and work. When you organize a complex project, optimize your daily routine, or troubleshoot a problem systematically, you're applying algorithmic thinking. Identifying repetitive processes that can be systematic and automated is another application of algorithmic thinking that can save countless hours. Evaluating trade-offs between different approaches to a problem, considering factors like time, resources, and quality, mirrors how we analyze algorithm efficiency. Even creating clear decision-making frameworks for your team or family can benefit from the clarity and precision that algorithm thinking encourages. Whether or not you ever write code, understanding how algorithms and data structures work gives you insight into the digital system that power our world and provides valuable mental models for problem solving in any domain. From bits and bytes to hardware components to algorithms and data structures, we've now explored the fundamental building blocks that make computing possible. In our next video, we'll examine how computers connect and communicate through networks and the internet, creating systems far more powerful than any single machine. If you're interested in learning more about algorithms and data structures, I really recommend this really practical approach in learning from the great book Grokking Algorithms by Aditya Bhargava. I don't know how to pronounce it, really hard to pronounce it. For a beginner-friendly approach, or explore other books that you might find in the reference in this video. What everyday problems have you solved using algorithm thinking? Let me know in the comments below. And if you like my video, please give me a thumbs up and also consider subscribing for more. This is Ivan helping you understand the technologies shaping our world. Thanks for watching, and I see you in the next one.